Hey guys, today we're going to look at Castle Unit 6, Activity 7, or Activity C6.7. The focus question for which is, does the total power output by the battery equal the total power dissipated by the resistors? Another way of phrasing that question that maybe you'll understand better is energy conserved in this electrical situation that we're looking at? Okay, that's really what it's asking. Is energy conserved? And so let's think about that focus question for a moment. It's telling us again that power is energy over time, the rate that energy changes from one form to another. And since energy is this conserved quantity with the ability to produce physical changes, the question is asking, can the energy from the battery just disappear? Or alternatively, can it go somewhere other than the resistors? Okay, there is actually a physical change that's happening, a transfer of energy that we can't technically see. The movement of charge through the wires is a physical change that is similar to moving objects through Earth's gravitational field. Lifting a pencil off of your desk is similar to moving a small amount of charge from one side of the battery to the other. Okay? So can the energy from our battery go somewhere other than the resistors, say the wires, or back into the battery itself, or something like that? Or could that energy disappear? These types of questions are what I want you to think about while you're writing your answers to those prediction questions that are on that sheet in front of you. So go ahead and write those answers, and then once you have those prediction questions answered, go ahead and proceed with the rest of the video. Okay, we'll take a look at the circuit that's on the left first, the one with two resistors in parallel. Okay, so here I have one battery. I have a 9-volt battery, and then a 50 and a 10 ohm resistor. So go ahead and take those down. The first thing that you should look at while you're filling out this table, the first little block, what is the voltage of the battery? What is the current through the battery? Okay, with that information, the voltage and the current through the battery, you should be able to calculate the battery's power output. Remember that power in the case of electricity is equal to the current I times V, the voltage. Okay, next record the resistance, voltage, and current for each resistor. Okay, so for my 50 ohm resistor, I have 0.18 amps of current. How much voltage do I have on this resistor? Well, it must be 9 volts since it's connected directly to the battery there. Okay, this whole wire we can call blue, and this whole wire we could call red. So the whole thing, that's 9 volts there. This is 9 volts here across this 10 ohm resistor as well. Okay, and then take a look at that, what you have multiplied out and added together there. Does the power dissipated by the resistors, that is, the power for this resistor and the power for this resistor, add up to the power output by this battery? Okay, let's take a look also at our series circuit here. First question, what is the voltage of the battery and the current through the battery? Since this is a single loop here with no junctions or nodes, that means that the current through the whole circuit must be the same. Okay, the charge can't just disappear, so the current through the whole circuit is 0.15 amps. We have, of course, 9 volts across the battery, so go ahead and calculate the battery's power output. And then record the resistance, the voltage, and the current for each resistor. Since I have 7.5 volts across my 50 ohm resistor, that means I must have 1.5 volts across my 10 ohm resistor. Both of them again have this current of 0.15 amps. go ahead and calculate the power dissipated by the resistors. Add that together. Does it add up to the same power output by the battery? Now, I'm going to go ahead and stop here for a second. Your answers to this question for both circuits should be yes. Okay? In this case that I'm looking at, with this series circuit and with that parallel circuit, the power dissipated by the resistors is equal to the power output by the battery. But there is a very, very important point that needs to be made here. And that is that this is a simulated circuit. I mean, to be more precise, it's a image of a simulated circuit. I'm not even simulating the circuit real time with you. I just took a screenshot of it. Okay? In this simulated circuit, it is an ideal situation where our battery has no internal resistance, so the resistance of the battery is 0, and the resistance of the wires is 0. In real life, that is not exactly the case, and we know that. We know that the battery does have some resistance, and that the wires, while they have a very, very low resistance, they still are there. They still have some resistance. There's charge moving through them. They do have a small amount of resistance. So if we include this resistance of the battery, which 1 ohm is the smallest that I can make it, and make the wires have a little bit of resistance, you see it's not quite the 0 right over here, it's a little bit more than 0. Okay, we see that the values actually don't add up. Okay, we can do some simple math here, right? 9 volts times 0.93 amps is not going to be the same as if we took these 7.77 volts and multiplied it by the same total current through these two paths, which is still 0.93 amps. Since, because of the way that this rounds, it's closer to 0.94, but that's okay. Okay, because what's happening when we have this resistance in the battery and in the wires is all of the voltage is not actually getting to these resistors. Okay, and so since they don't have the full voltage across the resistors, obviously it's not going to add up to the same total amount of power. But we also have some voltage in the wires, right? So what's happening here is the voltage that is not on the resistors, that voltage is getting used up by these wires here. Okay, because those wires do have a little bit of resistance. And some of it also is just getting used up by the battery itself. And so if we account for that and we add it all together, which I'm not going to do that for you here, if we account for the voltage that's across the wires and across the battery that doesn't make it to the resistors, if we count that, then the power values would add up. Okay, so as a conclusion, in an ideal circuit, the power dissipated by the resistors is equal to the power output by the battery. But in real life, when our battery and our wires have some resistance, some of the energy is going to be used up by the battery and the wires too, not just by the resistors in the circuit. If we do account for that energy loss within the wires, then the power supplied by the battery is equal to the power dissipated by the entire loop. And as our flow rate increases, the fraction of the power dissipated by the wires does increase, as in our parallel circuit here. Okay, in a series circuit, the amount of power that is dissipated by the wires is going to be a little bit less. And that's a similar concept to when we were adding more and more and more branches in parallel with our battery and seeing the voltage across each resistor drop. That's due to the internal resistance of the battery. One of the ways that you can kind of look at it is there's a lot of stuff moving through the wires, and even though it has very low resistance, the more stuff is moving through it, the more kind of friction is caused with those wires. So we do have to account for that as we get a higher and higher flow rate. Okay, I have one last little piece of notes here on interpreting voltage. This is kind of not directly related to the activity that we just did, but it's a little bit of notes that I want you to know about. Up until now, we have talked about voltage as this concept of electric pressure, as charge that is building up in one location or having a deficit of charge in another location. And the charge is kind of like air in that it wants to move from high pressure to low pressure. That is still a valid interpretation of voltage, but the more traditional interpretation of voltage is related to energy and power. If we look at this power equation, this V equals, or what started as P equals I times V, power is current times voltage, we can rearrange it to show that our voltage is just the quotient of power and current. It's power divided by current. Since power is a change in energy per second, and current is the amount of charge that moves per second, when we divide those, the time piece of each of them cancels out, right? So I basically have energy over time, and I have charge over time, which I know you guys aren't familiar with it, but charge is given by a Q. And when I do that division, my time cancels out. And so I'm left with this energy divided by charge. Okay, I'm left with energy divided by charge as voltage. So voltage is the amount of energy per unit charge. It's telling us how much energy our battery gives a certain amount of charge when it moves through that battery. It means that if I have a battery like this, okay, if I have a battery like that, and I take some charge right here, and I move it up to here, then I am giving that charge an amount of energy that is related to my voltage of my battery. So if this is like 4 volts, then every coulomb of charge that I move from here to here, okay, that's our unit for charge. Every coulomb that I move from here to here gains 4 joules of energy. Okay, so voltage is just telling us how much energy our battery gives that coulomb of charge when it moves through the battery. Okay, that's going to do it for us today, guys. Have a good weekend, I suppose, since this is our last assignment this week. We've only got like 2.5 more weeks left, so let's push through, guys. Later.